All right, good morning, everybody. How was your weekend? Or you want to forget about the weekend already? Fortunately, I didn't realize last week that the test was over the weekend. I thought it would be this coming weekend, but I just realized that you had the test last Saturday when I received an email from our lead TA that from Monday until Thursday we will be grading the FRQs for the test. So that's why I think I promised that we'll go over some more problems about Taylor polynomials this week. But yeah, that's without the knowledge of the exam being over the weekend. But insofar as the FRQ is concerned, I guess there are four problems in the FRQ. That means we will be grading until Thursday. We usually take a day for each FRQ because we are rotating the papers with the other TAs, so it will take us 4 days. So hopefully you'll get your FRQs over the weekend or early next week. But how was it? Was it hard or was it manageable? Students from my other class said it was tiring and it was a bit hard. So I haven't checked the FRQs that are assigned to me, but I'll start grading this afternoon. So yeah. Okay, but I guess you don't want to talk about it, so let's move on. Also, this is the last full week of classes. I guess the last day of classes is on Monday, May 3, and you will have a couple of weeks before the final exam. Do you already know what is the coverage of the final exam? Will it just cover the remainder of the course, or will it be cover to cover? I don't remember what was the usual coverage of the exam. But has Dr. Almus mentioned this already in the lecture or not yet? Because if the final exam will just be on the remainder of the topics, then we will try to focus our discussions with the remainder sections. Yeah, Brian, sure. That's my plan today. Oh, Christina, I see. Half is cumulative and half is over chapter 10. All right. So yeah, just let me know if you still have some questions about previous topics. But my plan for this week is to discuss and focus on on chapter 10, specifically for sections 10.1 and 10.2, because I saw that you were just given videos to watch for sections 10.1 and 10.2, so you didn't have sort of an interactive discussion about those two sections. So that's what I'll try to do today and probably on Wednesday. So we'll do 10.1 today. If time permits, we'll also try to start 10.2, but if not, we'll start 10.2 on Wednesday, because I guess 10.2 is important for 10.3, which is finding the area of polar graphs using integrals or integrating in polar coordinates. But yeah, let's start with the basics, 10.1. Have you guys had the time to watch the videos? Or you were too preoccupied with the exam and its aftermath, plus some other deadlines for other courses? Because if you haven't watched it, I can give you a detailed overview of those two sections. Okay, nobody wants to answer. So, okay, I'll take the safe route and give you a more detailed discussion about it, which will also be a good review for those who watch it already. All right. So, for most of, I think, your mathematical journey, you were only using Cartesian coordinates. We're in, we have the two-dimensional space. Hold on. Okay, there you go. Yeah, but two-dimensional space, and we said that all points in this two-dimensional space can be represented by a pair of coordinates, an x and a y coordinate, right? And how do we find those x and y coordinates? Well, we have a point of origin or the point of inference. We usually call it the origin, 0, 0, or the point of inference. And based on this, we get the x coordinates to be the directed distance coming from the origin in the horizontal plane. So the x coordinates would be this, and the y coordinate would be the directed distance coming from the origin with respect to some vertical axis. And with these conventions, any point on the space can be represented uniquely by a pair of coordinates, x, comma, y. All right. Well, now we will be using a different type of coordinate system, which will give us an alternative way of identifying points on the two-dimensional space. And we call it polar coordinates. Let me start this again. Oh, by the way, for today, I might turn off my mic on and off because I'm having some allergy attacks. So um, uh, don't don't think I left the chat if I just mute myself in the middle of a discussion, right? So I'll do it a couple of times. So I apologize in advance. But okay, for polar coordinates, we have also a point of inference, which we can also call the origin. But to distinguish it from the origin in Cartesian coordinates, I will call it the pole. And we have what we call the polar axis. Okay. And if we have a point in space, say this point over here, it will be represented by a set of coordinates as well, two coordinates, an r and a theta coordinate. And I look at the textbook and they use square brackets for polar coordinates just to distinguish it from the rectangular coordinates where we use parentheses. All right, so what does these two coordinates mean? So r is the distance coming from the pole. So if you measure this, that's r units. So that would be the r coordinate, or one way of getting an r coordinate, because you will see later that r can also be negative. But think of it as the distance coming from the pole towards the point. And then theta is the angle measured in the positive sense with respect to the polar axis. So this would be your theta components. And with these definitions of r and theta, will tell us that, oh, there are infinitely many ways of representing this point in polar coordinates, unlike Cartesian coordinates where we have a unique representation for a point. But in this way, if we define the polar coordinates this way, if this is theta, I can take another revolution around the unit circle or with respect to the polar axis, and I'll have r comma theta plus 2 pi, and that will represent the same point r comma theta. So that's one distinguishing feature of polar coordinates from Cartesian coordinates. You can represent a point in polar coordinates in infinitely many ways. One way to get another equivalent representation is to add a multiple of 2 pi into your angle theta. So you can do theta plus 2 pi, theta plus 4 pi, and so on. It doesn't matter how many revolutions you take, as long as you have the same distance r coming from the pole, you'll eventually end up at the same point r comma theta, right? But not only playing with theta, we can also play with r and get similar representation by using a negative value for r. And perhaps I'm gonna illustrate that later via an example. So let's see. Say I have the point, for instance, let's plot the point r comma, let me give a specific example. Say 2 comma pi over 4, okay, in polar coordinates. So in polar coordinates, it's theta, it's 2 comma pi over 4. I usually start by looking at the angle component or the angular component. So here the angular component is pi over 4. I look at the pi over 4 line here. So this is theta equals pi over 4, or you can label it here, theta equals pi over 4. And then the r component is 2. That means coming from the pole, here's the pole, I'll travel 2 units along the theta equals pi over 4 direction. So that means the given point could be somewhere here. Okay. Well, another representation for this point would be 2 comma 9 pi over 4. Because 9 pi over 4 will be this angle. So this is pi over 4. I add another 2 pi to it. Oops. This is pi over 4. I'll add another 2 pi to it. So that's going to be theta equals 9 pi over 4. But I'll still travel 2 units coming from the pole. So that means I get the same point, right? But as I have mentioned, you can also represent this point using a negative r value. So instead of a 2, I can use negative 2. But what's the effect of a negative r value? Well, for the negative r value, you will not plot it in the direction of the theta component, but on the direction supplementary to the theta component. So that means here, if theta is pi over 4, I will look at the opposite angle, which would be this guy. And let's see, that angle will be from here. Let me use a different color. From here until here, that would be 5 pi over 4, right? That's theta equals 5 pi over 4. Now, but I will not plot here because my r value is negative. Whenever the r value is negative, you plot in the opposite direction. So instead of doing it or plotting it at 5 pi over 4, I will travel 2 units in the opposite direction because r is negative. So here, I'll travel 2 units here. I'll end up at the same point, all right? So basically, the point negative 2 comma 5 pi over 4 also represent the same point. Okay. Now, there's an interesting relationship between the polar and the Cartesian coordinates. So here are our conversion factors or conversion equations. Okay, if you know the polar coordinates and you want to translate it into the rectangular coordinates, okay, so you know the r and theta component, then to get the x and y components, you can just use these conversions. X is equal to r cosine theta and y is equal to r sine theta, which is pretty straightforward because if you know r and you know theta, then just plug them in and solve for these values, right? One way to easily remember this is that the x component is always associated with a cosine, and the y component is always associated with a sine function, all right? Now, the conversion from rectangular to polar is a little bit more tedious or more involved because remember that if you have rectangular coordinates, which is unique, you can get infinitely many polar coordinates for it, right? So the conversion or the relationship here is that r squared is equal to x squared plus y squared. And again, the r value can take either positive sign or a negative sign. And I'll show you later how we can play around that. Okay. And theta is related to the x and y components via the trigonometric equation tangent theta equals y over x, right? Now I want to write, or I write the equation for theta this way, rather than writing it as theta equals arctan of y over x. Why? Because remember, arctan is only trapped within the first and the fourth quadrants because the value of arctan is just from negative pi over 2 to pi over 2. But remember that polar points could also live on the second and on the third quadrants, right? So if I will write theta equals arctan of y over x, that will tell us that theta will only be between negative pi over 2 and pi over 2, which is false, because theta could also be on the second or the third quadrants, okay? So that's why I prefer writing the relation for theta this way. And here we need to take note of the quadrant where theta lies. All right. Now let's look at some examples here. In worksheet 22, which I already uploaded a blank version of in my website, but I just copy pasted all the exercises from sections 10.1 and 10.2 so you can practice. But let's try to answer some of them. Okay. Okay. Let's start with the easy ones. So plot the following polar points. Okay, let's do problem 2. You can browse through the worksheet and let me know if there are some problems that seems interesting to you so we can answer them. But I plan to go over the even problems so that because I guess you'll get the solutions to the odd exercises. So I'll focus on the even ones. So for instance, number 2 is the polar point -3, 0. Okay. Now maybe I can use a single polar coordinates here. So oftentimes when plotting polar points, we either use concentric circles or a set of horizontal and vertical axes. But just to distinguish it from the Cartesian, I'm going to put the polar axis here. Just to remind you that this is in polar coordinates. And again, we're using square brackets here for polar points. So polar points, the polar point -3, 0. First, I look at the direction theta equals 0. Theta equals 0 is over here. Or perhaps I'll copy this first before I'll modify it. Okay. So theta equals 0 is here. So this is theta equals 0. But the R value here is negative. So I will not plot at theta equals 0, but on the opposite direction. Because I'm supposed to go 3 units or -3 units. So that would be on the opposite direction. So that will be going here. So my point would be this one. This is -3, 0 in polar coordinates. All right. So I hope that's clear. Let's try another one. Let's try -1/2, pi/4. Okay. Now again, I look at the angle component. That's pi/4. And let me draw the angle pi/4. So the angle pi/4 is here. Theta equals pi/4. But the R value again is negative, so I will not plot it at pi/4, but I will plot it at the opposite direction because I need to travel -1/2 unit. So from the pole, -1/2 unit along theta equals pi/4, so that will go backwards. So the given point will be somewhere here. That's going to be -1/2, pi/4. And then lastly, let's try a positive one just to complete the picture. Let's try 3, pi/6. Okay. Now again, I'll start with the polar component, pi/6, or the angular component. Pi/6 is 30 degrees, so that could be somewhere here. Okay. That's theta equals pi/6. And I'm supposed to travel 3 units along it. So 3 units somewhere, so maybe somewhere there. So 3 units along that line will bring us to 3, pi/6. Good? All right, so I hope that's clear. At least you get the picture of plotting polar points. Now, let's proceed to the next set of problems, which is to convert the following into Cartesian coordinates. So B, convert the following to Cartesian coordinates or to rectangular coordinates. And as I've mentioned earlier, this is pretty more straightforward than the reverse conversion. So for instance, let's try problem 8. We have -1, comma 2 pi over 3. Okay. Now remember here, the x component would just be r cosine theta. So you simply plug in the r and theta values. So r is -1. Cosine is, theta is 2 pi over 3. Okay. And then this would be -1 times what is cosine of 2 pi over 3? Cosine of 2 pi over 3 is -1/2. So this guy would be, the x component would be 1/2. Oh, no worries, Brian. If you missed a part of the discussion, you can watch the recording. This will appear in the MS Teams, and I will also post it in my website, all right? Okay, so that's the x coordinate. Let's compute the y coordinate. The y coordinate has formula r sine theta. And again, the r value here is -1. Then the theta component is pi over 3. So compute 2 pi over sine of 2 pi over 3. So that's going to be √3 over 2. So the x component is -√3 over 2. Right? So we can say that the polar point -1, comma 2 pi over 3 is equivalent to the Cartesian point 1/2, comma -√3 over 2. All right, all clear? Okay, let's try another one. Let's try problem 12. For problem 12, I have 1, comma 3 pi. Okay. Now again, the x component is just r cosine theta. This is r, this is theta, plug them in. So I'll have 1 times cosine 3 pi. Cosine of 3 pi is what? That's -1. So this would be -1. And then the y component is r sine theta. So this is 1 times sine of 3 pi. But 3 pi is equal to 0. Okay. So this would be 0. So the polar point 1, comma 3 pi is equivalent to the Cartesian point -1, comma 0. One way to double check your answer is to plot the points, because it doesn't matter if you use the polar coordinates or the Cartesian coordinates to plot the points, you will essentially get the same point, all right? Now, if we plot this in two-dimensional space, if I will use polar coordinates, I'll first look at the angle 1 over 3 pi. So this is 0, this is pi, this is 2 pi. So 3 pi is somewhere here. So let me note that here. So this is theta equals 3 pi. And then we're supposed to travel 1 unit along that line. So 1 unit there would bring us here. See, that's 1 unit from here, from the pole until that point. So that's 1 unit. But if you look at it from the Cartesian coordinates point of view, its x coordinate is -1. Just looking at the picture, right? Because here, this is on the negative x-axis, and the y component is 0, which is essentially what we got in the conversion. All right. So the lesson there is it doesn't matter if you use the polar coordinates or the Cartesian coordinates in plotting the points. So you should get exactly the same point. And this is a good way to check your answer, at least for some basic points, right? Okay, any questions so far? I hope this is clear. Can we proceed to the next section, or I mean to the next set of problems, which is converting from polar to rectangular, which is a little bit more involved than the conversion from rectangular to polar. All good? All right, let's try this. Okay, so the next set of problems will require us to find all polar representations for the following Cartesian points, with the emphasis on all. So because remember, for a specific point in Cartesian coordinates, there could be infinitely many polar representations. So we want to get a formula for the polar representation for the given points. So let's start with problem 14. Let's try the point 2, negative 2. Okay, now we can start with the r value. Remember that r squared is equal to x squared plus y squared. So plug in the x and the y components that we know. That will give us r squared equals 2 squared plus negative 2 squared, which would be 4 plus 4 will be 8. So that means r is plus or minus root 8 or plus or minus 2 root 2. Okay. And remember that we are allowing r to be positive, so I need to really take note of these two things. All right. So two possible r values, a positive and a negative value. All right. Now for the theta component, we have the following representation. Tangent theta equals y over x. This will tell us tangent theta equals negative 2 over 2. So that will give us negative 1. But before hitting it up with an arctan, all right, I need to make sure, I need to know on which quadrant right? So the x component is 2, y component is negative 2. So here is our point in Cartesian coordinates. So the theta component will be this guy, okay, which is in quadrant number 4. All right. Which is fine because I can if I use the arctan, then I would have gotten the right answer anyway, right? But what is the angle on the fourth quadrant whose tangent is equal to negative 1? So that would be 7 pi over 4. But this is just one of those angles, right? So you can choose theta to be 7 pi over 4 to begin with, or negative pi over 4 if you wish to use a negative value, right? Or this guy if you hit it up with an arctan. All right. Now, but remember that here we're looking for all polar representations. So in order to get that, I'll have two fundamental representations first. Two representations for the given point R. I'll start with two basic representations, and based on these two basic representations, I'll give the formula for all the representations for it. Now, what will these two representations be about? Well, these are the representations with the positive and the negative values of R. Now, the positive value of R is 2 root 2, so I'll use that as my first R. And the angle theta is the actual theta value that we got. So I can use 7 pi over 4 here, right? So again, this is the 7 pi over 4 angle. So this is theta equals 7 pi over 4. And then along that direction, I'm going to travel 2 root 2 units. So that will bring us from here, 2 root 2 units. That will bring me here, which is the desired point. So that's how I know, okay, I got the first representation correctly. But for the second representation, I want to use negative 2 root 2. All right. Now, if I want to use a negative 2 root 2, I will not travel along this theta. Sorry, I want still to travel along this theta value, but my theta unit here should be the opposite direction, right? So I'll be looking for this direction for this theta value. Perhaps I'll use a different color, right? So this would be my theta value for a negative value for r. Because if this is my theta value, all right, and my r value is negative, that means I will not travel in that way. But since r is negative, I'll travel in the opposite direction. So instead of going here, I'll travel in the opposite direction, leading me to the same point. All right. But what is this angle here? This is the angle supplementary to 7 pi over 4, right? So this guy would be what? This would be 3 pi over 4. Oh, am I using the right term, supplementary? Perhaps that's the wrong term. Supplementary, the sum is 180. So yeah, it should be the opposite direction. So you subtract your angle from 2 pi. Okay, so it should be in the opposite direction. They should make a 180-degree angle over here. Okay, so that angle would be 3 pi over 4. And this would be our two base representations. All right. Now to get all the representations, so any representation of 2 comma negative 2 in polar coordinates will be of the following form. Either it would be 2 root 2, comma, the first angle we found, plus a multiple of 2 pi to represent all the possible revolutions, right? So again, adding a multiple of 2 pi here will just make you go around the unit circle, some more revolutions, but eventually you'll end up with the same angle. So that's fine. Or you can use a negative angle and use theta equals 3 pi over 4 plus a multiple of 2 pi. So here you need to identify that k is an integer. It could be a positive integer, it can be a negative integer, but any of these forms will work as your representation. So this would be your general formula for the polar coordinates of the point 2 comma negative 2. And we are sure in the way we defined it that all representations will be of this form, right? We use a positive r value, we use a negative r value, then we add the multiple of 2 pi to the respective theta components that we computed. All right. Okay, perhaps one more example. Let's try problem 18. Now let's look for for the form of the representations for negative 2 comma 2 root 3. Okay. Now for this guy, r squared equals x squared plus y squared as usual. So r squared would be negative 2 squared plus 2 root 3 quantity squared. So this would be 4 plus 4 times 3. So that's going to be 16. So that means r squared equals 16 or r equals plus or minus 4. Okay. Then we use tangent theta equals y over x. That means tangent theta would be 2 root 3 over negative 2, which is negative root 3, but we need to take note where theta lies. So if we plot the point, the Cartesian point is -2, 2 root 3. So -2 is here. Say 2 root 3 is here. So we are on the second quadrant. So if you'll be looking for the theta component, that would be there. So theta is in quadrant 2. So hitting this up with an arctan formula will not work because arctan only gives us an angle between -pi/2 and pi/2, or an angle within the first or the fourth quadrant, right? Now, so what we have here is tangent theta equals -√3. So how do we get a -√3 out of ratios of values in the unit circle? You can think of it as √3/2 over 1/2, right? Maybe let's do it in our imagination. So something like this. Oops. I don't want you to confuse it with the multiplication. So, okay, perhaps I'll use an equal sign. Okay. All right. And then we are on the second quadrant. So we know that the x component is negative. So here we should have a -1/2. So we need to ask ourselves, what is the angle whose sine is √3/2 and whose cosine is -1/2? So if you go to the unit circle, so we're looking for an angle whose sine is √3/2 and whose cosine is -1/2. So that will leave me to 2 pi/3. So this would be our principal theta value. All right. Okay, so two representations for the point -2, 2√3 are the following, our basic two representations. First, I'm going to use the positive r value, so I'll use +4. And if I have a +4, then I'll travel along the theta direction that we identified. So theta we found out to be 2 pi/3. So there we go. That's this is theta equals 2 pi/3. And then to reach this point, I need to travel 4 units along theta equals 2 pi/3. Which is correct because we expected the point to be on the second quadrant. Now, if I'm going to use a negative value for r, okay, that means my theta component should not be this guy, but the opposite direction to it. So if I want to use a negative r value, I will use this as my theta component, right? But how do we find this? Well, from your angle here, you travel 180 degrees. So you simply add pi to it in order to get the new theta value, to get the opposite direction, all right? Or you could also subtract pi, but that will bring you to a negative angle somewhere there, right? I want to keep my thetas to be positive, but it's perfectly fine if you decide to to use them, one of them to be negative. So here, from 2 pi/3, I travel additional pi to get to the opposite direction. So that will give me my second theta value, which is 5 pi/3. All right. And this is a valid representation because my theta value is 5 pi/3, so that is somewhere here. But I won't travel in that direction because my r value here is negative. So instead of traveling here, I'll travel in the opposite direction. So I'll travel 4 units in the opposite direction, and I'll end up with that point. All right. So that's how I get these two basic representations for the point. And using these two representations, I can get a formula for all of the representations. So any polar representation for -2, 2 √3 would be of the form. Start with your first representation and just add a multiple of 2 pi to the angular component. And copy the second form, but then again add a 2 pi or a multiple of 2 pi to the angular component and say that k is any integer. All right. That's our representation for this polar for the Cartesian point. Okay, is it good for now? Okay. Now let's try to bring it a little bit further and look at converting entire equations into polar form, right? So I guess here they are problems 27 to 34. Let me see. Okay. All right. So let's try some of these. Okay. Let's try problem 31. Well, let's start with the basic ones. Problem 27. So here, this is what we will be taking advantage of. R squared equals x squared plus y squared. And what else? X equals r cosine theta. And y equals r sine theta. I guess these are the more useful conversion factors here. I included this guy because before performing substitutions, I will try first to see if I can isolate an x squared plus y squared. Because if I have a complicated expression, then the x squared plus, if I can get an x squared plus y squared out of it, then I can simply replace it by r squared. But it is equivalently correct to just replace all x's and y's you see by x equals r cosine theta or r equals sine theta. For instance, in problem 27, I can just say that, oh, x squared plus y squared, I can replace it by r squared. And then the right-hand side remains 16. So I'm done. R squared equals 16. That's the polar representation. Or you can do it the long way. So you have x squared plus y squared equals 16. If you will be relying only on these two conversion factors, then you will have r cosine theta quantity squared plus r sine theta quantity squared equals 16. And to get this representation, you need to play with a lot of algebra and trigonometry here. So you can simplify this as r squared cosine squared theta plus r squared sine squared theta. Loss of exponents in play there, right? And then I can factor an r squared, leaving with cosine squared theta plus sine squared theta equals 16. But I hope you remember this. This is the right-hand side of the Pythagorean identity, right? Cosine squared plus plus sine squared is equal to 1. So this entire thing, this guy is just equal to 1. So I'll have r squared equals 16, which is exactly what I got by simply using x squared plus y squared equals r squared. All right. So that's why I suggest manipulate the given expression or the given equation first and see if you can get an x squared plus y squared so that you get a more elegant form for the solution. Because this is a very elegant and simple way of representing the equation. This is already in polar form, but not yet in simplified form. So if you are asked to find a simplified representation of the solution or to identify what type of equation you have, it would be helpful to have a simpler representation. Okay, let's try problem 28. Oops. I guess for problem 28, you have x squared plus y minus 1 squared equals 9. Okay. By the way, guys, let's see. So we know that this is a circle centered at the origin with radius 4. Okay. And since this is the same representation as this guy, so these two guys should represent the circle with radius 4. So now you will see here that you could have written this as r equals plus or minus 4, but actually I say that you can just ignore the positive, you can ignore the negative root and just say it's r equals 4. Because if you do the graph, if you're looking at it from the polar point of view, this is true for any theta. So for any angle, 0 to 2 pi, the radius should be equal to 4. So that means radius is equal to 4, radius equal to 4, radius equal to 4, radius equal to 4. So this is my basis. This is 4 units. This is 4 units. This is 4 units. This is 4 units, right? If I want to get what are those points that are negative 4 units away from the origin, I will also have this because this is negative 4 units if I'm traveling at the opposite direction. So that's why we were able to ignore the negative root. And then you can trace the circle out. We get this circle, right? Oops. Okay. So in problem 28, we're dealing with another circle, but a more complicated circle. This is the circle centered at 0, 1 of radius 3 units, right? Let's see how it looks like in polar coordinates. Again, you could start by replacing all x's and y's by the by r cosine and arc sine theta. So again, you can write this as r cosine theta quantity squared plus r sine theta minus 1 quantity squared equals 9. But it doesn't look very simplified, so you need to put some more work to get its simpler representation. What I want to do here first is to carry out the expansion because I know that from here I will get a y squared. And that y squared combined with the x squared outside can be just r squared. So what I'm saying is I can expand the second term on the left as y squared minus 2y plus 1 equals 9. And oops, I have an x squared there. So, but first I can write it this way, equals 8, right? And then x squared plus y squared can be replaced by r squared minus 2. Since y is alone there, I cannot have an r squared anymore. So y will be replaced by r sine theta equals 8. And this would be my polar form for the equation, right? And then that's one difficulty of working with polar coordinates because we are not familiar in spotting or in identifying the graphs of certain functions in polar coordinates. Because if we have not done the conversion, then we will not have an idea that this simply represents a circle centered at 0, 1 of radius 3. And that's what would be the motivation for the next set of exercises. We will be given polar equations and we will translate it into the Cartesian coordinates in order to identify their graphs. So those are problems, I guess, problems 35 to 36, right? Because if you look at these equations, they look nasty, right? And it would be difficult for us, if not impossible, to identify how the graph looks like without converting them to polar coordinates. Okay, and that's where we will start next time. We will work some problems out from problems 35 to 36. But if you haven't done so, please watch the video for 10.1 and 10.2, and then try some of the problems from 1 to 34 from worksheet 22. And then let me know on Wednesday if you have some problems with some of them, and then we'll discuss them. If you don't have any questions, then I'll start right away with some of the problems from 35 to 46. All right, is that a good plan? I hope it is. So, all right, guys. So again, try some problems and let me know if you have some questions on Wednesday, all right? So thank you for coming today. Let's see each other again on Wednesday. Bye, guys.